All right, so section 1-2 we're going to cover in 2 days. Let's see how far we get here. The first question, and this entire chapter really deals with functions and their graphs and their properties. There's a lot of little details. You have got to start studying on a daily basis. It's becoming quite clear as I graded your tests in the last chapter that, some of you didn't even know the quadratic formula, and I gave you a song for Pete's sake to go with that.
You sing it?
No. So you've got to start doing some daily reviewing of your notes. And you've got to use your notes as you're doing your homework. Some of you quite clearly did not take notes yesterday based upon some questions I had today in the last class. So your notes are a tool. They're not something for you to do here and never look at again. You're creating a study guide, a helpful pathway for you to do your homework in. All right, so the first question, and by the way, I can't possibly give you an example of everything that's in your homework. So one of the other purposes of doing your homework is so that you can cover more material that perhaps I couldn't get to, and then you ask questions on that. So your homework is vital because it will have things in there that I didn't cover in notes. Question 1, does the formula y equals x squared define y as a function of x? So you're going to see a lot of function notation in pre-calc. Calculus uses it a lot, and so you won't see me avoiding it. And really what this is, I might seem to be missing quite a few colors, that's why. The x is your input. The y is your output. So if y is a function of x, that can be written to where it looks like this. F of x is equal to x squared. This is my input. This is my output. So yes, y is written as a function of x. F of x is a fancy name for y, the function of x, f of x. So all we've done is replace y with f of x. The right side of the equation is still the same. Y, f of x, is being defined in terms of x. So yes, this is correct. So answer yes. So they might just ask you, so if I had x is equal to y squared, and it was asking you, is this defined as y as a function of x? The answer would be no. X is equal to y squared is solved for x. X is being defined as a function of y. So know the difference. Example 2. Of the 3 graphs shown, which we're going to draw them, which is not the graph of a function? So, before we can do that, let's talk about tests for a function. Hopefully we can answer this question. Period 2 was silent. Vertical line test, what is that? Who would like to share? Hands raised. Nobody wants to share. Thank you, because otherwise I wasn't going to explain it. Describe it in terms of a graph. So we take a vertical line. Here's my vertical line. What do we do with that vertical line in the graph? Move it along the graph, and I'm looking for, if it's a function, it only hits the graph once at any place, if it's a function. If it's not a function, it's going to hit it in more than one place, right? So let's look at the following graphs. This first one looks like this. The second one looks like this. And the third one looks like this. That's my favorite. Which of these pass the vertical line test? Does this one pass it? Yes or no? Yes. Yeah, if I move my vertical line anywhere along that graph, it never touches it more than once. So this, yes, is a function. What about this one? Is there any vertical portion to that graph? It's made of, the only difference between these graphs is this is a curve and these are straight lines, right? Are any of the straight lines a vertical part? Nope. So this passes the vertical line test because there's no vertical portion to the graph. What about this? if and I'm just going to draw a vertical line through here. I could have chosen any other place other than I certainly don't want to choose over here because you could prove it's a function by putting your vertical line over here where it only touches the graph once. But the problem is if I move the graph anywhere else, now it's touching it 2, 3, or more times, right? And so because it's touching the graph 1, 2, 3 times, all I have to do is find one place where my vertical line test does not work and it's not a function. So this one is no. That's the one that's not a function. Now I also threw in here the other test for functions. If you're looking at ordered pairs, right here, we're looking for x values to not repeat for it to be a function. So if you think about the x value here, notice that the x here is 2 and the y is what? 2, 4, 5. So this one's 2, 5. This ordered pair here is 2, 0. See how the x is repeating? And this ordered pair here is 2, I don't know, negative 4.5-ish. So here my x values are repeating, not a function. Y values can repeat all day long. That's okay. But not x values. All right, so next example. Now we're going to explore domain. You should have done this in Algebra 3-4. A little bit. We're going to do a lot of this in pre-calc. A lot of it. What is domain? There you go. So domain refers to only x values. So we're looking for the x values to be restricted. We're looking for restrictions on the domain. Restrictions occur on x values with square roots and denominators of fractions. So let's start with A. You're to determine what the domain of this is. They might give you the graph and not the algebraic equation, or they might give you the algebraic equation and not the graph. It's much easier to look at the graph so long as you can tell what values there are. And usually they'll mean one. So here we're going to do it algebraically because you might not have the graph. So anything, what values can I take the square root of? None? I can take the square root of 4. But in general, what values can I take the square root of? Positive values. What about 0? Can I take a square root of 0? Sure, square root of 0 is 0. Nope, square root of 0 is 0. What times itself twice gives you 0, 0, 0, right? So you can't take the square root of 0. But I can't take the square root of a negative number, correct? So anytime you have a radical square root, you want to take whatever's underneath, and in this case we have x plus 3. That value of x plus 3 underneath must come out to be greater than or equal to 0 for us to be able to take the square root of that. Notice I'm not saying that x itself has to be greater than or equal to 0. The value of x plus 3 together must be greater than or equal to 0. So solve that algebraically. Subtract 3. Doesn't x have to be greater than or equal to negative 3? Because if x is negative 4, let's just say, what's negative 4 plus 3? Negative 1. Can you take the square root of negative 1? No. If x is negative 2, what's negative 2 plus 3? 1. And you can take the square root of 1. It's 1. So my point is x can be negative. It just has to be negative 3 or greater. So let's look at our graph. We're going to take our calculator. See if I can get the glare off of it. And we're going to go to y equals and put in the square root of x plus 3. The older calculators, you might have to end the parentheses under square root and then hit graph. What do you think that point right there is? Negative 3. If you're not sure, you can either find your 0, or you can go to your table and put in negative 3. Sure enough, it's a 0. So I'm going to start plotting some points on here to make my graph. So at negative 3, 0. If I put in negative 2, which is the next integer, I get a nice happy integer point. So negative 2, positive 1. And if I put in negative 1, I don't get a happy point, so I'm not going to plot that. 0, I don't get a happy point. 1, I get 2. So 1 gives me 2. Because 1 plus 3 is 4. Square root of 4 is 2. And that's enough for me to get a good shape to that graph. And so when we describe the domain, most likely you're going to have to describe it in interval notation. We worked on this in the last chapter, correct? But I want to focus on if I had just given you the graph, I want to look at my x value, so I start from the left and I go to the right. From the left, I have no x's, no x's, no x's. Finally, I hit this first x value, which is what? -3. And then doesn't x just continue to get bigger and bigger and bigger? There's no end to this, correct? So my left bound point is what? What's my leftmost point? -3. Do I include -3? Yes. So it's a bracket. And it goes through to positive infinity. So your domain starts at -3 and goes to positive infinity for your x values. So it didn't ask it, but I'm going to go ahead and talk about range on this one as well. So range goes up and down, because that's your y value. So typically we'll start from our lowest y and go up and see where there are restrictions. So if you think about it, this is my y value. What is the only type of value or answer I'm going to get from a square root? What answer is going to occur when I take a square root? You're going to get what kind of answer? Positive, right? Or 0. So as I go from the lowest y value and start working up, what's the first y value I hit? Right here, that y value at that point is 0, isn't it? The x value is -3, but isn't the y value 0? So my y, my range, starts from 0 and continues to go what? Up into what? Positive infinity. So my range, they didn't ask this, but my range would be, do I include 0? Is 0 included with that solid dot? Yes. So I'd have a bracket at 0 and I'd go to positive infinity. Didn't ask for the range, but we're going to look at it in the story anyway. You will in your homework. So range is from down to up, and domain is from left to right. Don't go the opposite direction. So you want to go from smallest to largest values. All right, look at the next one. So for this one, we've been given not only a radical, but we have a denominator. What do you know about a denominator? What value can a denominator not be? It can be negative. 0. This denominator can never be, we cannot split anything. The denominator is telling you how many groups to split something into. So if I have a denominator, let's say, I don't know, of 2 over 0, that's saying that take 2 items and split it into no groups. Can I take 2 items and split it into no groups? I have at very least one group of 2, don't I? I can't have no groups of nothing. I don't think that was probably English, but we won't go there. Don't tell my mother. She's an English teacher. But I can take nothing and split it into 2 groups. If I have nothing and I split it between the 2 of you, how much do you each have? Nothing. So I can take nothing and split it. We have nothing. But I can't take something and split it into nothing. If anybody tells you that you're nothing, it's not true. You are something. You can't take yourself and split you into nothing. You're at least one thing, right? Didn't I uplift you, make you feel so much better? I know. No, it's such a boy answer. Huh? I'm confusing you. Can I take 2 things and split it into nothing? Logan.
Logan's like, shut up.
Logan, I've got $2.
Okay.
Can I split my $2 amongst no groups? Because at most I have the money, don't I?
Yeah.
So it's in one group of me, 1. So I can't take 2 things and split it into no groups because it's already one group as it is. So if you're going to take something and divide it, it's already one group before you divide it. So I can't take something and divide it into nothing. But I can take nothing and split it amongst multitudes, right?
Okay.
Everybody would have nothing,
Yeah.
but I can still split it.
Okay.
That's a great thing about nothing. I can split it. But I can't take you and split you into nothing. All right, so here we go. So I have a restriction on the denominator. I also have a restriction because of that square root, just like we had over here. So we have two different restrictions we're looking at. So first restriction, we're going to look at this one. What do? Don't square it. We're not solving. No, we're not multiplying. What do we do over here? We took what was underneath the square root and we set it greater than or equal to 0. So same thing here. We're going to take what's underneath the square root, in this case x, and we're going to set it greater than or equal to 0. Would you agree that if I choose a value for x, if it's not 0 or positive, I won't be able to take the square root? And so it doesn't matter. I mean, if x in the denominator can be a -2, which it could be, I can't put a -2 in the numerator because I can't take the square root of -2. So we have to combine those restrictions. So x must be greater than or equal to 0, and then the lower restriction for that denominator, take the entire denominator and set it not equal to 0. Because we don't want it to be equal to 0. So solving algebraically would add 5. So x cannot be equal to 5. X can be anything we want it to be, but it can't be 5. The minute x is 5, 5 minus 5 is 0, and we cannot have 0 in the denominator. So we have to combine this restriction with this restriction. So x has to be greater than or equal to 0, but just not 5. So it creates this kind of hole. So let's look at what the graph looks like, and then we'll write our interval notation. So go into y equals and clear that out. And we're going to put in, be careful when you put this in, square root of x. Make sure you get out from under the square root sign, or close your parentheses if you have the older calculator. Divided by, use parentheses, x minus 5. Hit graph. Notice that our restriction is x must be greater than or equal to 0. Are there any negative x's here? No. Nope. No negatives here, right? The graph actually starts, the first x that we come to is at the origin. Let me see yours. He has the older brick calculator, just slightly older version of mine. Oh yeah, okay, good point. So the older calculators and then the new colored calculators do this as well. This is your asymptote, your vertical asymptote in here, and it's annoying. They took it out on my calculator because it would annoy. It looks like a heartbeat blip, doesn't it? Yeah. But the new colored graphing calculators put it back in. I personally don't like it in there because it interferes. It's not really part of the graph. But if you see that, that just means it's a vertical asymptote.
Yeah.
Well, it depends on how you, yeah. Yes. Let me see it. So if it doesn't graph, it's because your stats plots are on, right? And so if we go up here and hit enter, we'll turn that off, and then we'll graph it. There you go. And yours is doing that asymptote thing too. All right, so we good? Are you good? Okay, everybody good? Yes, dear. Let me see. This is good because somebody out there in the world might have the same issues. Mostly because it looks like your scale is different than mine, right? So if you go to zoom standard, because it's only showing, it's blowing up this part of the graph only. If you go to zoom standard, now it's going to show the other parts that you're missing.
Okay.
Does that make sense?
Yeah.
Yep. All right, so we all good? All good points. All right, so here we go. Let's go ahead and graph it. So we know we have a vertical asymptote here at x equals 5. So we're going to go ahead and put that in there. So that's one of our restrictions. The other restriction that you can't tell is there is actually a horizontal asymptote, but we'll get into that later. So I know that there's a point here. I'm going to take out my little scribble that accidentally got on here. Some of you that's going to bother if it's there. All right, so this goes this direction and hugs that asymptote, and then we just have a little bit here that's showing. So let's write our interval notation for our domain. As I approach from the left, 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 what's the first x value I come to? 0. Does it include 0? Yes. So bracket at 0, and I continue with my x until I hit a fence I have to jump over. What is that fence? 5. So I don't want to include 5, so I have parentheses. Now you're going to have to pay attention to what MathXL wants. They might want a comma here. I like to do union. But they might want a comma, so you have to pay attention, read the directions, and see what they want. And then we jump over that, so the fence that we jumped was 5, we're not including it, and we keep going until, what's the right bound? Where do I stop? Infinity. So this is the domain that we're looking for. They didn't ask for the range, but we're going to go ahead and talk about the range. As I go from bottom to top, what's my lowest y value down here? Negative infinity, right? And it goes up, 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 up. It looks like there's an asymptote here, but can't x be 0? Yeah. And, well, for our purposes, because you don't know how to find horizontal asymptotes yet, we're just going to assume whether or not there is on any of your graphs, unless you distinctly clearly see one. And this one's not necessarily distinctive, is it? Because it looks like it's approaching 0, but it could be approaching a half. We'll work on that later. All right, so our range for our purposes here, it doesn't appear to be restricted, does it? Does it? No. It's going from negative all the way to positive. So our range would be negative infinity to positive infinity, until we look at it in more detail later. All right, the last one. Yes, sir. The U here, it's a U for union. When you do your MathXL, they might want a comma. They might only want the intervals. On my test, you're going to put a union, because you're telling what all the values of x are. Seth?
So if it asks for intervals, it's
Probably a comma.
solution.
Yeah.
Yes.
Right. I would use a U unless otherwise stated. And if it's not working after you punch it in, because you have 5 tries in your homework in this chapter, not 10. And if after time 2 it doesn't work, stop. Don't waste your tries. And then ask me the question. We'll work out, figure out what's wrong. Yes.
So for A, why wasn't the range negative infinity positive?
Because as I go from the bottom, there's no y's here, right? There's no y values here. The first y value I encounter is a y value of 0, because this is the first point I encounter from the bottom of the graph, and the y value at that point is 0. And if you think about it, because I'm going this way, there's my cut, right there's at 0, and I get to positive infinity.
That's not the case for the
This one I'm going from negative infinity because I have a point here, right? And it's going forever in that direction. That's why I know it's negative infinity, because it's an arrow and it doesn't stop. Does that make sense? Okay. Yes.
Did you turn the examples off or something? I mean, like on the homework, because like.
Oh yes, I did, because you can cheat through your whole homework by using the examples. You can open up a second screen and just have it answer it for you as you go down there. You don't learn anything. Whereas similar example is different. Yeah, because it. No. Too bad, so it's not. So, to alleviate the cheaters of the world, unfortunately for some of you, I took the example out, because it will solve it for you. And if you open up a second screen and then it doesn't know that you turned on the example. If you turn it on in the same screen, then it gives you a similar example. But if you open up a separate window and have them side by side, you can cheat with that. So, unfortunately. Oh, the cheaters are smart enough to do that. I know. I totally agree. I totally agree. Because you want to learn. That's why. Because your goal is to learn, right?
Yeah.
The cheater's goal is just to cheat and not learn anything. And then they fail their test. And they're like, but I got the homework correct. Smart in that respect, but not smart because now they're going to fail their test. So overall, yes. All right, so let's continue. We'll continue this afterwards. Is this for this example? Okay, so let me continue with this. So as you look at, are you good? Okay. So look at the third example. Notice that the third example I've now switched. I don't have f of x or g of x. I have this a of s. So s is actually your x value, just the s. The s right here means that we're calling x now x. So this is your x value. The a of s, the whole thing, that's your y value. That function notation. A of s is your y value. The s itself is telling you that that's our input, and x is always our input. Is the variable in a denominator? No. Is the variable underneath the radical? So there's no restrictions on a variable. There shouldn't be. So let's look at the graph. Once your y equals. And be careful. Use parentheses. Make sure you get out of the radical 3 before you hit divided by. And if you have the older calculator, you'll have to close your parentheses for that radical, so you'll have double parentheses. Divided by 4. And then x squared. Don't use an s squared because your calculator still thinks the x-axis is x. And then hit graph. Shocking that it's a parabola because s is raised to what power? Second. And it appears the vertex is at what point? 0. So let's go into second graph and put in 0. What do we get? 0. So if I put in 1, 2, 3, 4, 5, I don't get any nice points, right? Okay, so I would just worry about plotting 0, 0. And you're going to plot your parabola. Because really 0, 0 is the most important point. Yes? Say that again? What did I do? What? Oh, gotcha, that. You have the older calculator, so you probably have to have double parentheses. Because you have a parentheses around all of this, but you also have a parentheses for your square root of 3. Does that make sense? Right? Are you good now? Okay. All right, so as we travel from left to right, what's my leftmost x? Because this is going to get bigger and bigger and bigger and bigger, right? In negative infinity. What's my right? Positive infinity. So your domain for this one is negative infinity, positive infinity. It is unrestricted. So you might want to write that here, that there are no restrictions on x. There are, however, restrictions on y. Y is restricted. To what values? Yeah, as you go from the bottom, you work your way up, the first y value you come to is 0, because at that point, 0, 0, which is the minimum, the vertex of this parabola, the y value is 0. And the y value just gets bigger and bigger and bigger, doesn't it? So if I were to ask you what is the range, you would say the range is equal to 0 to positive infinity. So interestingly enough, this is an unrestricted range, but a restricted domain. This is an unrestricted domain, but a restricted range. Are we good with that? Any questions on domain and range? All right, so let's flip it, and I have one range question. Since we've talked so much about range, I only chose to put one range question on here. So we're going to find the range of the following function. We have to make a correction here. This is not supposed to say y. This is probably when the lights went out. The lights went out in Phoenix. And so that should be 2 over x. Now there are restrictions on x. What can x not be? Yeah, x cannot be 0. So we know the restrictions on the domain would be x cannot be 0. And that's a domain restriction. Let's see how it affects y. Before you type it into your calculator and look at the graph, do you think there's any value that y could not be? Think of it in general terms. Can y be negative? Y is your f of x. Can the value of this fraction be negative? Yes, if x is what? Negative. So if x is negative, y is going to end up being negative. Can my fraction be positive? Yes. Can my fraction be 0? Why can it not be 0? Correct. The numerator is what makes a fraction 0. Is there any fraction in the numerator? There's no way that numerator can be 0. So I'll guarantee you the restriction on the domain is actually going to be 0. Because it can't be. So let's look at what the graph looks like. So go to y equals, put in 2 divided by x, and hit graph. Not only do we have a vertical asymptote of the y-axis, but we have a horizontal asymptote of the x-axis because x can't be 0, right? And y is not going to be 0. So it creates those two asymptotes. So our graph looks like this. As x becomes a bigger and bigger number, so as x goes to the right and becomes bigger and bigger and bigger, doesn't the value of that fraction become smaller and smaller and smaller? That's your y. Same thing occurs as x becomes more negative but bigger negative. Y is still going to become a smaller and smaller value negatively. But consider the space in between -1 and 0 and in between 0 and 1. If x is a fraction itself less than 1, what is 2 divided by 1/2? Multiply by the reciprocal. 2 divided by 1/2. 4. So the smaller x becomes, the larger y becomes. So the smaller x becomes, the larger y becomes. So that's why this graph is acting the way it is. All right, so our range. Where's our range restricted? 0. So as I go from the bottom up to the top, I've got, what's my bottommost number here? -infinity, and then I skip over 0 and go to positive infinity. So my range goes from -infinity to 0. Does it include 0? No, because we're skipping over it. Union 0 to positive infinity. Wouldn't this also be my domain? Just as an aside. All right. Continuity. Let's go ahead and talk about that. Continuity is huge in calculus. And it helps us with limits as well. So let's draw some graphs here. I've got all the graphs labeled, we don't have them in, so we're going to talk about them and draw them as we go. So continuous at all x. For a function to be continuous, it has to be a curve. They're probably not going to give you a graph with straight lines in it, although I'll see what happens in the homework. I'd be surprised if they did. But draw the following. This is a graph that is continuous at all x. It is a nice, smooth curve with no breaks in it. No breaks. Bless you. It is continuous everywhere. Meaning all x values. We look at continuity based upon x, really. Now we have two of them that are called removable discontinuity. They look similar but have one slight difference to them. So put a hole at -3, -3. Put a hole there. And create a similar looking graph as the one that we just did. And then you're going to put a closed circle at -3, +4. This is called a removable discontinuity. And it's at In this particular case, it's at any particular x value. I'm going to call this x value a. In this case, we know it happens to be -3 just by looking at the graph. But the function is not defined at a. Technically it is because we plugged this hole up here. So at -3, the function actually does have a value of 4, but it's a break from this continuous curve because of that hole. So it's called a removable discontinuity because we remove the discontinuity by plugging that hole. So the graph itself is discontinuous because of the hole, but we remove the discontinuity by plugging it. So you can put in here the hole is plugged. Yes. Correct. Yep. The x's for both of those have to be the same. Because if this was moved over 1, there's no y value associated with that x value. Good question. All right, then the other type of removable discontinuity, put a hole again at -3, and draw exactly the same graph but without the plug. This is still considered a removable discontinuity because we could plug it if we wanted to. You like that? Even though we'll need a little bit more room for this one. Even though the hole is plugged, we could plug it. To make, what's wrong? Oh, thanks. Even though the hole is not plugged. Sorry. Thank you. I was like, what?
Sorry. I'm not my test.
Okay, there. Just put it right there. Is not plugged. We could plug it to make the graph continuous. There you go. Thank you for tracking. And you're going to have to know what type of discontinuity these graphs are, so that's why you pay attention to the differences between them. Then we have this thing called a jump discontinuity. So put a hole at -2, 0. Put a solid point at -2, +3. And then the graph looks like this. The difference between the removable discontinuity graph and the jump discontinuity is the fact that the graph itself is not continuous without the plug. So if I took the plug away, the graph itself is not continuous. So if I took the hole away, the graph itself is not continuous. Whereas if I took the hole away here and the plug, the graph itself would be continuous. So because we have this jump, this space in there, that causes the jump discontinuity. And we're going to look at limits with these same graphs later, which I'm going to introduce you to the limit notation today. You won't use it much yet. But before we get there, again, this is still A. So this value here is still A. So the graph is discontinuous at A. And then infinite discontinuity, we've already seen today. It occurs with vertical asymptotes. So we're going to put, and your textbook probably won't put the asymptote in there, but we are for note purposes. So it'll look something like this. And we've seen this today already. So again, the curve itself is not continuous. There is no plug on this one. And I'd have to make a jump to get from one curve to the other. It's not a jump discontinuity though. These are visually different looking. This one has a hole in the plug. The infinite discontinuity does not. So questions about the differences of those. And this, by the way, is A again. It's discontinuous at A. So then let's look at some terminology. It's not going to mean a whole lot to you yet, but I wanted to introduce it to you so that it's not quite so horrific when we get to it. A function f is continuous at x equals a if, and here's the notation, if the limit as x approaches a of the function is exactly equal to the value of the function when a is plugged in. So in other words, if you can find a value for a, for the function, it's continuous. But the function is discontinuous at that value where x is a, if it's not continuous there. So in other words, if there's a hole or an asymptote, it's not going to be continuous. Like on here, our a probably would have been maybe here, let's just say. There's a value that I can plug in for a into the function and get an exact value for it. This one, technically, I can get a value for a, but it's because a hole's been plugged. We'll look more into that later. But I just wanted you to see that notation. We're going to view more of that notation as we go along. That's what you use in calculus all the time. Questions before we flip? Okay. So, example 5. So based upon those discontinuities, judging from the graphs, which of the following figures shows functions that are discontinuous at x equals 2? We're specifically looking for discontinuity at x equals 2. If there's a discontinuity at x equals 3, that's not what they're looking for. All right, so here's your first graph. Let's put a vertical asymptote there, and then the graph looks like this. You may or may not have the name of the function or the algebraic equation, so this would be x plus 2 over x minus 2. Is that function discontinuous at x equals 2? Yes or no? Yes, what kind of discontinuity? So this is an infinite discontinuity. So that one's a yes. If I had moved that asymptote to x equals 3, then it would have been no, because it is infinite discontinuity at x equals 3. So be careful for those shifty little differences. All right, the second graph for B, put a point on the x-axis at -3, on a point at +2, a y-intercept of -6, and the vertex is going to be like just a smidgy right here. This happens to be a parabola. Well, the y-intercept is not the vertex. And then the function is g of x is equal to x plus 3, x minus 2. Is this graph discontinuous at x equals 2? No. What kind of continuity is it? It's continuous. It's continuous everywhere. Now, if I had put a hole over here, right here, your answer to this question would still be no, because it's discontinuous at -2. So be careful with how they ask the question. All right, last graph. Put a hole at the point 2,4 and put a solid point at 0,2, the y-intercept. And then connect a line, but not through the hole off of either end. This is the graph of h of x is equal to x squared minus 4 divided by x minus 2. Here's how a graph of appears to be a quadratic can end up looking like a straight line. This quadratic factors into x plus 2, x minus 2, and it cancels the x minus 2 down here. So all you're left with is x plus 2. So it mimics a straight line of x plus 2, but because x cannot equal 2 in the denominator, because it would make that denominator 0, there's a hole right there. And if you were to graph this on your calculator, it's not going to show the hole on your calculator. It'll show it in your table of values, but it's not going to show the hole. So if I put parentheses x squared minus 4 and parentheses divided by parentheses x minus 2. So if I put this into my calculator and hit graph, do you see a hole in my graph anywhere? So be careful of that. But if I go into my table and I put in 2s, I'm looking for discontinuity at 2, what happens? It says error. So your calculators don't show the holes. You have to be aware that they're there. So you have to be a little smarter than the calculator sometimes. So this would be yes or no. Is it discontinuous at x equals 2? Yes or no? Is there a hole at x equals 2? So it is discontinuous. So the answer is yes. What kind of discontinuity is this? Flip in the back. It's not a jump, because I don't have a space in between. I don't have my graph is not broken. If it were a jump, I'd have like part of the graph up here. It'd look like a piecewise graph. This is a removable discontinuity. Even though it's not plugged, I could plug it. So it's a removable discontinuity. So this one's yes too. And then I think I'm going to stop there. So this is the end of J1.